My name is Chen Kai Li. I'm a professor in the Department of Computer Science and Engineering at the University of Texas at Arlington. The rest of the authors of this paper are my current and former students. For various reasons, none of them can be here. So you end up hearing me presenting this work to you. But it is these students, they did heavy lifting in carrying out this work. Our paper is concerned about knowledge graph completion. I do not need to motivate this audience about the importance of knowledge graphs in powering AI applications. However, one of the challenges we face in using knowledge graphs is the lack of completeness in knowledge graphs. So for instance, consider this example knowledge graph in which the fact that the movie Roseland was directed by James Ivory is missing from the graph. Now, with such incomplete knowledge graph, our applications will have troubles in doing fantastic things, such as making recommendations of movies to a user if the user already likes other movies directed by James Ivory. So the goal of knowledge graph completion is to find the missing link between the entities and complete this graph. There are actually various formulations of knowledge graph completion tasks. One of the most extensively studied form of knowledge graph completion task is link prediction. And here is a diagram that shows the workflow of training and applying a link prediction model. Right, so you have a bunch of triples that represent the relationships between subjects and objects. And then you learn a link prediction model on the training data. And then you apply this model given a relation and an object as the input. And this model will rank candidate entities based on how likely they can be the subject that is missing there. That is what link prediction does. So there have been many machine learning models for this task. The very first one that popularized the link prediction task is the Chen-C model, which was published 10 years ago. And this paper has been quite influential with more than 7,000 citations. There have been a lot of follow-up work, various models that attempt to improve the state-of-the-art performance of link prediction. And as you can see, this table here on the slide summarizes some of the more well-known models, and they have been quite influential as well, with quite some citations. In evaluating these models, so by the way, one of the most extensively studied types of link prediction models are embedding models, and that's the focus of our paper. So in evaluating these models, people have used the various evaluation metrics. Some of these measures, they are defined in such a way that a higher score, a larger score indicates a better performance, a model with better accuracy. Some other measures are defined in the opposite way. Right, so one example is MRR, mean reciprocal rank, and the filtered mean reciprocal rank. So these are measures in which a larger score reflect a more accurate model. These models have been evaluated using various data sets, and here is just a list of representative ones, which I'm fairly sure you're quite familiar with a lot of these data sets. Now, our paper wants to answer this fundamental question. How do these models perform on large-scale data sets? Surprisingly, this question was not satisfactorily answered in the literature. There have been a few publications that reported the results of various models on several data sets. And so the only one that is derived from Freebase. The only large-scale Freebase dataset is Freebase 86M. And this dataset is problematic. Particularly, it has so-called non-subject matter triples, which I shall explain momentarily. Right? And there are two datasets derived from Wikidata. They do not have triples that represent multi-relationships, relationships, which I shall also explain momentarily. Now, I won't get into the details, but our focus in this paper is on Freebase. And I do not want to make any false claims with regard to Wikidata, but as of now, we are actually in the process of doing a similar study using Wikidata. Now, you may ask, Freebase maintenance has been stopped for 7 or 8 years. Why are you still using Freebase? That's a very fair question. The fact is, Freebase remains the single most frequently used dataset in the study of link prediction, by far. So we looked at publications in CS Rankings conference in 2022. There have been 53 such papers last year. And so this is the list of those conferences. So these papers focus on knowledge graph completion. 48 out of the 53 use the datasets from Freebase, and only 3 of the 48 use large-scale Freebase datasets, and particularly they used Freebase 86M. As I mentioned earlier, it is problematic. Out of the 53, 8 publications use datasets derived from Wikidata, and 5 of them use large-scale versions of Wikidata. In a nutshell, all these benchmark datasets, they either are problematic or small, or they do not capture real-world data modeling idiosyncrasies. And I'll explain very soon what I mean by data modeling idiosyncrasies. So you may also ask, why are you so obsessed with the dataset being large scale? And how large is large? That's also a very fair question. The fact is, models, they perform drastically differently on small and large scale datasets. So in this slide, we have a table summarizing the performance of 5 representative embedded models for link prediction. The second column here reports the results of these models on the original FP15K dataset used in the Chen C paper. And we now know this dataset is problematic because it has the data leakage problem with a lot of reverse triples, right? If you take out those reverse triples, you get this dataset called FP15K237. And there, as you can observe, to perform all these models degenerates quite significantly, right? Some of the models were supposed to outperform Chen C on FP15K, but most of them actually do not show any improvement if you evaluate them using FP15K237. And arguably, the absolute accuracy of these models is quite poor, right? So one may wonder, can we really use these models in real-world settings? Okay. Now, in the last column, you will see the results of evaluating these models using one of our newly created full-size Freebase datasets. And what's interesting is that if you look at the performance, by the way, all these numbers are in fMRI. So if you look at the last column, these models, the results more or less become consistent with the originally reported results on FP15K. But that is only a coincidence, right? Because they're evaluated on 2 very different data sets. Now, I should also mention that the performance of these models are implementation or library dependent. Right? In this column, you will see the results on libkge are quite different from the results of these models using implementations from DGLK. Okay. So to our best knowledge, DGLK is the only library that can accommodate knowledge graphs with hundreds of millions of triples. So these are the only results we have. We don't really know whether they will perform quite differently when we evaluate them using a different library. But these results are not known before, right? And that ties back to the question I asked earlier. How do these models perform on large-scale data sets? And for the first time, our paper reported such results. So here I just want to summarize the contributions of our paper. We, for the first time, reported link prediction models' true performance on full-size Freebase datasets. That's number one. Number two, we reported how their performance is affected by various data modeling idiosyncrasies. There are several, with regard to reverse triples, multi-array relationships, and type system. I'll use the rest of 2 or 3 minutes to briefly mention some of these. And then we made our data sets available. So these are thoroughly prepared full-size Freebase data sets. And they could be useful for tasks beyond link prediction. So just some of the details that I skipped earlier. Right here, you will see a radar chart comparing these 5 models on Freebase 86M versus one of our newly created data sets in which we only retain subject matter triples. So what are subject matter triples? In Freebase 86M, 31% of the triples belong to non-subject matter domain. So they are not about knowledge facts. They are actually about how the data set was created, curated, and managed within Freebase. And so that's quite different from knowledge facts. And I would argue they should be separated, evaluated from the subject matter triples. And you can observe the performance of these models actually became quite much worse if you mix together non-subject and subject matter triples. So in Freebase, most of the triples, they actually came into the data set in pairs. Right? For instance, there is a triple about James Ivory being the director of Roseland. There's a corresponding reverse triple about Roseland being directed by James Ivory. And the fact that these two relations are reverse relations, are actually captured in Freebase using a special relation called the reverse property. And this is useful for various purposes, right? But we need to be really careful when we evaluate link prediction models using a data set with such reverse triples. Because otherwise, you could have one relation in training data, and then when you evaluate model in your test set, you could have the other relation. And that's a serious data leakage problem. As we observed already earlier, and the performance would degenerate quite significantly after you remove the reverse triples. And here, the radar chart showing the effect of with and without reverse triples. Okay. So what is multi-array relationship? In Freebase, it's called a CVT or mediator nodes, right? It represents a relationship between several triples connected through this intermediate node. Actually, most of the relationships in Freebase, and most of the relationships in real world are multi-array relationships, right? And in FP15K, FP15K237, and so on, these multi-array relationships are just concatenated into binary relationships. And the problem with that is after concatenation, you have a data set with information, certain information lost. For instance, if James Ivory got a bachelor's degree from University of Oregon and master's degree from Southern California, after you do the concatenation, you will actually not be able to figure out necessarily from where he got his bachelor's and master's degree, respectively. The reason being, you have other people who graduated from USC and Oregon with both master's and bachelor's degree, right? So they're all connected. Now, this table just shows you the effect of having multi-relationship concatenated into binary relationships. There are a lot of details, but the conclusion is that if you do such concatenation, the link prediction problem kind of gets easier, if you compare this column with that column. Okay. So I'll skip the details about Freebase type system. I would encourage you to read the papers about what exactly it means and what we did about Freebase type system in our data set. And the effect of using Freebase type system in helping improving the performance of link prediction models. So this is a summary of the data sets we created with regard to the different data modeling idiosyncrasies. This one doesn't have the multi-relationships. This one doesn't have the reverse triples. This one has the multi-relationship. It doesn't have the reverse triples, and different statistics of the data set. And you can observe their difference on these models. So just kind of a repeat of what I said earlier, right? So this paper, for the first time, reported link prediction models performance on full Freebase data sets and studied the impact of these idiosyncrasies on their performance. And we made the data set available that could be useful for other tasks. And then you can find our source code, data sets, and results on this GitHub repository. And I'm ready to respond to some questions. Thanks for listening.
Thanks a lot.